ahead and get started. It's my extreme pleasure to introduce Pawel Hawrylak today. He's been a long-term friend. Our paths seem to have followed each other in parallel in many cases. He's now at the NRC. He started off at the University of Kentucky and then went to Brown. He's been at the NRC for about 25 years. He leads a theory group at the NRC, but it's a theory group that's heavily involved with a variety of the experimental efforts that go on there. We're looking at single electron qubit devices. Pawel has done a lot of the foundational work towards understanding excitons and semiconductor quantum dots, excitons and magnetic fields, excitonic complexes. He's now moved on to other sorts of quantum dots, and he's going to tell us some combination of that work. Thank you, Pawel.
Thank you very much, Garnet. Thank you, Glenn, for having me here. So I will tell you a little bit about what we have been doing in Apple over the last couple of years on both semiconductors and graphene quantum dots. And so why are we doing it? Because there are many challenges. They are different for everybody. Some of the challenges in the ICT sector can be summarized in the following way. So if you look at the current semiconductor technologies, you have silicon for electronics, you have compound semiconductors, such as indium phosphide, indium arsenide, for optoelectronics or for communication, yes? And you have ferromagnets for memory. So you have very different material systems that you need to bring together for an ICT device such as this laptop. And of course you have lots of wires. You require a lot of elements, for example indium, which is in short supply. And so it's not sustainable from the point of view of the materials. There are still seats here up front, gentlemen. It's also energy inefficient. That's one of the biggest problems. Yes, you have lots of wiring, lots of ohmic losses, lots of other problems which make these very energy inefficient devices. And of course, they are not powerful enough, which is why we have places like Joint Quantum Institute. So, how many of us try to address this challenge? Well, one way is to build a different type of quantum computer, so use new quantum principles. So that's one way to go around the challenge. Another one is to cut some of the wiring and put memory directly into a semiconductor. So that's semiconductor spintronics, use spin for information processing, build directly memory, so ferromagnetic semiconductors. So, and so that would be semiconductor spintronics. Perhaps a different route is in changing technology and going to completely different new materials. So maybe printed electronics for some of the many consumer-oriented applications, maybe a different solution. And there are seats here. And so that requires also different materials and different fabrication routes, moving away from the epitaxial growth, or new materials, for example, carbonics. So everything is cut. So we have been trying to work with devices that to some extent address these areas. One is devices based on two-dimensional electron gas in gallium arsenide, where you localize electron spins and try to build quantum circuit based on these electron spin qubits. We work with indium arsenide, indium phosphide dots. So this is a schematic picture. You create a dot, you control precisely its location, its size, and you can put gates around the dot and you can functionalize this device. We work with indium arsenide gallium arsenide self-assembled dots, where we developed an understanding of excitonic artificial atoms making quantum dot lasers, amplifiers, and so on. We are working also with quantum dots where one puts individual magnetic ions, so tries to control these magnetic ions by interaction with light through excitons. We are also working on nanocrystals, so this is moving from epitaxial growth to colloidal growth, so nanocrystals for solar cells, and one of the interesting problems is multi-exciton generation. And we are now working on carbon-only based quantum dots, so these graphene quantum dots and topological quantum dots. I will be discussing physics with my fingers for most of the talk, but we have a computational tool which we call QNano, and we start with a structure. We calculate strain. Usually there is strain, so through atomistic calculations we determine the position of atoms, and this we do for about 1 billion atoms, and then a variety of electronic structure calculations and response functions through configuration, interaction, and eventually physical properties, so either solar cells or high excitation optics. So let me start with describing some of the work that we have been doing on these electron spin qubits. So we started working on this in early 90s, and then in 99 we learned how to count electrons in these devices, and 2000 we created the first electron spin qubit, and of course then that followed with a double quantum dot device, and of course there is a lot of work in various other groups, so Charlie Marcos and Seigo Tarucha. About 2005 we built a first triple quantum dot, which is now investigated, and well, the idea is that eventually one will build a quantum lab. So this is a well laid out path, but perhaps there is some other way forward. And so I will describe work that's done mainly by Yun-Pil Shim, who is sitting here. You'll raise your hand. All right. And we will be talking about changing the direction for these transistors, field effect transistors, changing the direction of a technology of a say, $100 billion industry. How can we do this? Well, standard transistors are classical devices. And why are they classical? Because the ground state is continuously connected to excited states. So they decohere very easily. And that's why they are classical. So can we create a macroscopic quantum state? Basically like a superconductor, but in a field effect transistor. Okay. So you can start with so there is a transistor, it has source, it's a gate, it has source and a drain, and it has a gate, and imagine that you will take your nano drill, and in this gate you will drill little holes. Okay? So you will drill little holes, and what you apply negative voltage to a structure with underlying to the electron gas, and what this will do is it will localize electrons in these holes. Okay? And what you want to do is you want to create a chain of electrons, a one-dimensional chain of electrons. This does not create or open a gap. There are spin waves, and so the ground state is still continuously connected to the excitation spectrum. What you need is these additional electrons or additional quantum dots for each pair of electrons. And what does it do? So imagine that you create this chain of localized electrons, and they are necessarily coupled antiferromagnetically. And now for this pair we bring a third dot, a dot with a singlet electron system. And this dot acts effectively like a source of RKKY interactions. And when we couple it, you can induce ferromagnetic interaction in your electron chain. So we start with our structure. We create now ferromagnetically coupled pairs, which are antiferromagnetically coupled. And now it's obvious what will happen. We can replace this by an effective spin 1 chain. And what this leads to? It leads to an artificial Haldane gap material. So if you look at the gap separating the ground state and excited states, then whether it's a spin 1 chain or this ferromagnetically antiferromagnetic coupled chain of spin 1/2 particles, you approach a gap in the thermodynamic limit, and that's the Haldane gap. And what this means is that the ground state, so it's like making a semiconductor out of this spin chain, but the difference is that the ground state is fourfold degenerate. It acts like two spin 1/2 particles. So you have a fourfold degenerate ground state that's protected by a gap from the excitation state. And you can dial it in or out by just using voltages in your field effect transistor. Now, so that's one thing that would be nice to realize. I would like to talk a little bit about emergence of topology in interacting electron system using these artificial quantum dot molecules. So actually this issue of topology and geometrical phases dates back to a very nice paper by Herzberg at NRC, already I think it was 63, and then of course followed by a beautiful paper by Michael Berry. So of course we are also celebrating the concepts of geometrical phases in condensed matter physics with Charlie Keynes and Shouchen Zhang and Duncan Haldane's Dirac medal. These are all one electron effects. Can we observe topological phases in interacting electron systems, and can we do these in a controlled environment on a chip? So let me show you, maybe somebody knows why this is so, show you how this works. So let's imagine that I build a quadruple quantum dot structure. Let me put one electron in each of the dots. Okay? And if these electrons are spin polarized, let me now take one out and create a hole in this complex. Okay? So I create a hole in this complex, and now I will look at the tunneling of this hole. Okay? So I look at the tunneling of this hole to go from that dot 1 to dot 2. The transition matrix element is just tunneling matrix element, T, one electron matrix element. And we go and tunnel until we get to the second to last dot. Now we tunnel from dot 4 to dot 1. This only can take place if this is a connected geometry, connected topology. It cannot happen in a linear molecule. And when we do so, the matrix element is again T. So you can easily solve for the energy spectrum. You find the ground state for this 3 electron complex in terms of this hole. And now we look at the same complex, but now we flip the spin. So nothing has happened really dramatic. It's just a single particle behavior. Now let us flip one spin in this 3 electron complex. And now let's look at this hole which is moving in this spin 1/2 electron complex. So this spin 1/2 3 electron complex can be characterized by chirality, collinearity of these 3 spins, and this can be understood easily in terms of spin current. So I can think of this minority spin up, moving on this plaquette, and direction of the motion of this minority current determines the chirality of this 3 electron complex. So the hole now is dressed by the chirality. It carries the information about the minority spin current, or the spin current due to minority spin. And now if I go and look at the tunneling of the hole dressed by chirality. Okay, nothing happens here, but when I come to the end of my chain, and now I want to complete this circle, this hole tunnels to the beginning, and the tunneling matrix element acquires a geometrical phase, which is related to the chirality. So it's only present due to interactions, or it's only present because of internal degrees of freedom of the electronic system or the background in which this hole moves. And well, you can calculate the energy spectrum. It's very simple. You will find that this ground state is an excited state of a system, so the ground state is spin polarized. But the important thing is that this tunneling matrix element, a tunneling or one particle matrix element, T14, distinguishes between spin. And so somehow, by tunneling from on a circle instead of tunneling on a chain, we distinguish between a spin of the electronic system. And this phase can be thought of as originating from an artificial gauge in just the same way as artificial gauge appears in geometrical phases in the Paris phases. So that would be an interesting system to investigate, and perhaps the cold atom community might be interested in this. So some other things that we have been working on is a chirality-based qubit at a half-field triple quantum dot, a generation of entangled states, and generation of Berry states. All of this is on chip. Okay, so we have some sense of what we can do with electron spin qubits in gallium arsenide and field effect transistors. Let's now look at new materials. What could we do with that? So, as I said, one of the challenges are these three different functionalities. So if you want to build an efficient ICT circuit, you have to be able to do electronics, you have to be able to do photonics, and you have to be able to have magnetism or spintronics, and preferable in one material system. So can we do this and therefore cut all these wires and make a really very small system? So it's like molecular electronics, but just with cutting. So can we make a graphene-based integrated quantum system? So let me just remind you why graphene is interesting. Actually, graphene, we hear a lot about it, but graphene was, theory of graphene was developed at the National Research Council of Canada in 1946. And even though the title of the paper is the then theory of graphite, it was mostly about single layer or graphene. And Wallace predicted correctly the structure of a single graphene layer, predicted the fact that there are two non-equivalent atoms, two atoms per unit cell, so that there are two sublattices, defined the tight binding Hamiltonian. So we are talking about 1946, so we are approaching 50 years, and predicted the linear dispersion. Because we have learned in these 50 years many things, and so our abilities, experimental abilities, this theoretical understanding is really enriched by these 50 years compared to what we knew as scientists in 1946. So there was a lot of work, of course, and Słonczewski, McClure, and both Jean and Mildred Dresselhaus. So there's a lot of work on graphite and graphene. And in the 80s, there was a realization of a effectively single layer by intercalation. So when you bring in atoms in between carbon layers, you push them apart, you donate carriers, and this was called graphite intercalation compounds. There was a lot of work, and there was another seminal paper by Blinovsky which described optical properties of graphene. stage 1 intercalated graphite, where the layers are independent. It's the optical properties of graphene. And this is an example of a measurement done by Peter Eklund at the University of Kentucky. Well, you have the linear dispersion, and it's a p-type doped structure. So Fermi level is in the valence band, and so you have an threshold for an onset of absorption. This is experimental results with some theoretical fits. That was just learning to walk. About the same time, we also developed a theory of collective excitations. And for example, for a bilayer graphene, one predicts a shift for inter-subband plasmons by hundreds of millielectronvolt due to electron-electron interaction. And if you have a multi-layer graphene, then you expect a surface plasmon that only starts at some finite wavelength. Today, of course, it's a wonderful field. I like to think of this step by Andre Geim and Kostya Novoselov and Philip Kim and many others, and Horst Stormer, as a similar step as for semiconductors, when one moved from bulk doped semiconductors, which were the basis of electronics from the 50s to the 80s, to modulation doped semiconductors. And we know how moving dopants away from free carriers led to discovery of new phenomena, for example, fractional quantum Hall. And so I think that this current status of graphene is equivalent to the modulation doped gas of Dirac fermions. Why is graphene special? I presume you all know this, but just in case, you have two sublattices. Yes? And you can think of an electron propagating in one direction, and if it's a properly chosen direction, the wave function will only be on red sublattice. If you now turn back and start propagating in the backward direction, you have to switch from red to blue sublattice. And not all scattering centers can do this, and so you have very high mobility, and this is why the first experiments by Andre Geim were so exciting. Now there is another interesting point that is kind of obvious, that if you have Schrödinger fermions, then the kinetic energy scales like 1 over length square, and the potential energy scales like 1 over r, and so there is an Rs parameter that scales the ratio of Coulomb to potential energies, where Rs is an average separation between electrons. And so for small Rs, high density, it's really a non-interacting electron system. But for Dirac fermions, both the kinetic energy and the potential energy scale in the same way, and the coupling constant, or Rs, depends on the screening by external environment, epsilon, and Fermi velocity. So there is no density dependence. We are equally ignorant at all densities. So just to summarize this, because before we jump into quantum dots, why is it interesting for me to work on graphene quantum dots? We start with graphene, and it's a 1 carbon atom thick, so kind of hard to get thinnest than that. Carbon, so there is a potential for no nuclear spin, so all the hyperfine coupling or the decoherence due to coupling of electron spin with nuclear spins can be removed. It's carbon, unfortunately, so there is no magnetism. Okay? So kind of hard to make a magnet out of a carbon. Well, there are Dirac fermions, so we have seen it's interesting. Dispersion analogies with quantum electrodynamics. There is sublattice. Sublattice meaning two different states, so it's pseudospin. And with a pseudospin, you have various phases, geometrical phases. Klein tunneling, Well, it's something that makes working with graphene quantum dots a little harder, because you cannot confine carriers with gates. If you try to confine an electron and there is a barrier, an electron will convert into a hole under the barrier and then come out as an electron again. There is edge physics, and that sort of is new, known from mid-90s, but it's an important physics. And there are electron-electron interactions, which are a little different than for normal Schrödinger electrons. So it's good to keep these features in mind when moving forward. So graphene is, as we know very well, it's a semi-metal. So if you want to make a device, you need to be able to turn it off. So you need a gap, and so you need to create ribbons or dots or edges to induce gap through finite size effect. So I will be talking about what can we do with this graphene quantum dots. So how do we do it, or how do people make these graphene quantum dots? The simplest way is in Klaus Ensling group is to simply carve out of graphene structures where you can make a quantum dot and it's connected to the rest of your leads, which are again graphene. You can grow graphene on metallic substrate. This is iridium, and you can see that you can create clusters of carbon with well-defined size. This is a very nice process by Liang-Shi Li at Indiana University, where they make carbon quantum dots using colloidal metals. And they have measured absorption, emission, and optical properties of these structures. One other way, which comes from Pawel Hawrylak from MIT, is cutting graphene. So this is now a top-down approach, but in a funny way. You can put a nickel nanoparticle on top of graphene, and this nickel nanoparticle will walk on this graphene and cut bonds. And it will cut bonds according to crystallographic directions. And here are examples of structures which you can create this way. And nobody believes in this the first time, but there are other groups at Oxford, for example. Andrew Briggs' group is also doing the same. They have reproduced this result. I personally don't understand exactly how this works, but there's some statistical mechanical process by which this nickel particle moves around and cuts the bonds. All right, so I have a graphene and I want to cut it. We can cut it in two ways. So you can see that one way to cut it is called armature. It looks a little bit like an armature. And another way to cut it is a zigzag. So you can create two types of edges of graphene. Understanding edges is very important in finite structures. So now we want to take graphene and we want to make a semiconductor out of it, because we want to embrace the semiconductor industry. So we will make a semiconductor out of graphene. The first thing is we want to open a gap. So we take this graphene quantum dot, and it has armature edges, and we will solve a one electron problem for electron hopping from one atom to another, and there is a tunneling matrix element that connects nearest neighbors. And what we did is we simply diagonalize this Hamiltonian. And one has an energy spectrum as a function of the Eigenstein index. Yes? And so what you see is we started with a continuous energy spectrum of graphene, with the density of states that was vanishing at the Fermi level for graphene. But now we see that a gap opens up in the spectrum. And we have some shells of energy levels. In fact, we have these double degeneracies. They are not related to speed. These are doubly degenerate HOMO and LUMO levels. and in most of the structures that we studied, there is this double degeneracy. In a macroscopic dot, in a quantum dot that's derived from effective mass equation, the degeneracy is natural, it comes from Wally degeneracy. This is not a Wally degeneracy, but it's related to the two values. So you have a doubly degenerate HOMO and LUMO level, and that controls optical properties. So now what we do is we take these different structures and we study their properties as a function of size. So what I am showing here is the gap of these quantum dots as a function of size. So we go from somewhere around hundreds of atoms to about 1 million atoms. And you see that the gap shrinks. For the larger structures, the energy is measured in terms of these tunneling matrix elements, or the bandwidth of graphene, somewhere of the order of 2.5 to 3 electron volt. And so this would be somewhere around 2.5 to 3 electron volt. So this is green, blue approaching UV. And you can tune the gap just by changing size from visible or from UV to terahertz. So what this means is that one covers the entire family of semiconductors. So some examples of semiconductors are here. This would be a gap of silicon. This is a gap of typical indium arsenide quantum dots. These are lead selenide nanocrystals. And we can continuously tune the gap by just changing the size. So that's quite interesting. I think we can cover the entire family of semiconductors and all the compound semiconductors that you have to work so hard to tune the gap off and fit your specific applications. For example, you can cover the entire solar spectrum. Right? So you see here this linear dispersion on this logarithmic scale, and this linear dispersion is actually fitted extremely well by just taking a Dirac fermion with energy v times k, Fermi velocity times wave vector. Wave vector is 2 pi over lambda, where lambda is wavelength, and I will fit half of the wavelength into my quantum dot for the conduction band and half for the valence band, and you get a gap that's inversely proportional to the diameter of the dot, or inversely proportional to square root of the total number of atoms, and that's exactly what this is. So we can understand this behavior of the gap for armchair quantum dots fairly regular in a simple way. Now, do the properties depend on the edge? So here we are moving from armchair to zigzag, and we do the same, and we see this is the same shape, the same number of atoms, but a different edge. So by changing the edge, we change the dependence of the gap on the size or on the number of atoms. It's quite a significant difference. Right? So by changing the edge, we can engineer the electronic properties. Can we change the electronic properties by changing shape? And here we are deforming this zigzag-edged quantum dot to a triangle. And we calculate the band gap, again up to millions of atoms, and we find that this is the band gap. Okay? So again, it's the same edge but different shape. You have different dependence of the gap on the number of atoms. So from this, we see that we have at our disposal these three tools. We can control electronic properties by size, by shape, and by edge. So it seems like we started with just carbon atoms, but now the variety starts appearing. There is a little more of this variety which will become apparent in a moment. So this is a spectrum of this hexagonal quantum dot with zigzag edges, and you see, okay, this is the gap that we were showing across the Fermi level. You have some almost continuous band of states grouped into little shells, but there is nothing dramatic about it. If we look at the energy spectrum of this triangular quantum dot, we see that there is a dramatic difference. A large portion of the spectrum now collapsed into this shell of degenerate states. Okay? So what we were showing as a gap was this transition from top of the valence band to the bottom of the conduction band, but we did not mention the existence of this gap. In the middle of the gap, you have a shell of degenerate states. Okay? So everything was very simple until now. So you have this shell of degenerate states, and when you see the degeneracy, you wonder, is this accidental, or is this real? Is this controllable by the size? And what one can show is that this degeneracy is proportional to the size of the triangle, and so it can be made macroscopic. So this is a very nice system where we can design a macroscopic degeneracy. And if you have a macroscopically degenerate state, then you know that there can be magnetism there. All the properties will be controlled by electron-electron interactions, because that's the only energy scale left in the problem. It's like having a lowest Landau level, okay, and electrons in this lowest Landau level. So maybe there is some analogy with fractional quantum Hall effect, but at zero magnetic field. Okay. So this is an interesting system to also look at the interacting electron system. So what is different between the hexagon and the triangle is the sublattice symmetry. When I said we deformed the hexagon to the triangle, it was not correct. There was a difference of a number of atoms, and this difference of number of atoms, I think it's 22 in this particular example, is exactly the difference between the red and blue atoms. So by deforming the structure, we break the sublattice symmetry. So we can classify these quantum dots by either having sublattice symmetry, the same number of A atoms as B atoms, or having different numbers of the two sublattices. Well, it is important to at some point when it's getting exciting, to see whether these structures are real. So you do ab initio calculations, and sure enough, without doing anything, you have reconstruction of the edges. Yes, so you have 5 carbon atoms, 7 carbon atoms. The edge, zigzag edge, is not stable. Not stable because you have dangling bonds. This carbon atom has only 2 neighbors instead of 3 neighbors like this one. So you need to passivate the surface, and that becomes tricky. How do you passivate just the edge? But I presume that smart experimentalists will find a corner of the phase diagram where you will just add hydrogen atoms to the edge and not somewhere to the center. So when you do this, then you have a perfectly stable zigzag edges, and we can proceed with the analysis of the properties of these triangles. So the first thing that we want to show is the simplest, and that is that if I take these any of those quantum dots, I will examine the triangle because it's the most interesting. That if you examine such a triangle and you bring in a gate, so this is a picture of a gate which controls the carrier density on this carbon triangle, then we can control the current by the applied voltage to the gate. Okay. That's your transistor. Well, it will be single electron transistor because it's a finite structure. So, in order to understand how this works, we need to compute. And because we have this degenerate shell, we don't know how to compute. So there's no meaningful approximation to the energy levels on a degenerate shell as a function of shell field. So what we do is we first empty this shell. In a charge-neutral structure, there is one electron per state of this degenerate shell. So we empty it, and then we have a gap. So we have a Hartree-Fock ground state. There are all the field levels protected from the rest of states by a gap, Hartree-Fock gap. So we start with this Hartree-Fock ground state, and then we bring in electrons by the gate to this degenerate shell. And we study the interaction of these Hartree-Fock quasiparticles using exact diagonalization technique. Yes? So first we determine our single particle levels by tight binding, then we calculate all the Coulomb matrix elements, and then we use Hartree-Fock to determine Hartree-Fock levels, then we rotate our Hamiltonian to a proper quasiparticle interacting Hamiltonian, and then we use exact diagonalization to study properties of this shell as a function of the filling factors, filling of this shell. So if we for all the graduate and undergraduate students, so if I am doing numerical work, how am I going to look at these results? What's the best way to look at these results? So one way is to look at the gap. So energy gap of this degenerate shell for different electron numbers. Okay? So if I don't have interactions, then for any number, for example, 4 electrons, I can put 14 electrons for this particular shell. At 4 electrons, the gap will be 0. Yes? Because it's a degenerate shell, and I can put 4 electrons on 4 states with equal energy, and I can move an electron, and it will cost me no energy. So the gap is 0. And of course, it doesn't depend. This doesn't depend on the number of carriers. So this is the gap as a function of shell filling. It does not change. Now, if I turn on interaction and look at my system again, I see a dramatic difference. Yes? The gap as a function of shell filling, or the number of added electrons, oscillates as a function of shell filling. So electron-electron interactions determine the ground state and the excitation state. Now we can compute conductance of this quantum dot as a function of gate voltage. So here is a calculated conductance of this dot as a function of gate voltage, and you of course have Coulomb blockade, and this Coulomb blockade, so the change of the current through the quantum dot as a function of gate voltage, with amplitudes, the probabilities that depend on how the electrodes are connected. Yes, we have some finite system with atoms. The actual variation will depend on where we connect, but overall dependence, overall fact that we can control the current through the dot by the gate voltage will remain. So we can do electronics. What about magnetism, or what about building a magnetic moment? Well, we see that if we look at the gap as a function of number of electrons, we see that at half filling the gap is the largest. If we now look at the total spin of the ground state as a function of number of electrons, we see that at half filling the total spin is the largest. So the shell behaves just like a atomic system with Hundsuits. Like electrons come in, and they all come in with parallel spin to minimize or minimize energy or take advantage of exchange energy. Okay, so they just build up the total spin. And so the ground state looks like a spin polarized state with 1 electron per state. And if you look where the net spin polarization is, it's predominantly localized at the edges. So you can look at as a function of size of this triangle, and you see that the existence of the spin polarized shell does not depend on the size, at least within the sizes now. So we understand this in the following way. If you take graphene and you create a zigzag edge, you will get spin polarization. This is known. But these spin polarized states are immersed in a continuum of other excitations. If you bring two edges together in a ribbon, you have spin polarized edges, but there is an antiferromagnetic interaction. So if you come with a screed, you will see no magnetic moment. On the other hand, if you cut a ribbon, a triangle, you get ferromagnetic interaction between each edge, or a net magnetic moment. Now, can we tune this magnetic moment? So imagine that I have a triangle, it has a magnetic moment, and now I will bring another triangle. And it will either have a magnetic moment or spin that's polarized in the same direction as the top triangle or in the opposite direction. So for that we need to do calculations, and we find that the two magnetic moments are ferromagnetically coupled. Now we apply electric field, and this electric field will allow us to turn this magnetic moment off, because as we increase electric field, electrons from the upper triangle will want to tunnel to the lower energy triangle, and in order to do so they have to flip their spin. So now when I go and measure the spin, it shouldn't be there. Okay? So we can turn this magnetic moment on and off with an electric field. That's also an interesting new functionality. New, but it's a functionality that might be interesting. If you make these triangles a little different, yes, that what we were talking about was a maximum polarization at zero electric field, both spin polarization, both top and lower triangle have net spin. But if we choose our sizes differently, then we can, by applying electric field, just place a single electron on one of the triangles. Okay? And so, without being in contact with an electrode, which is a source of tunneling, of various decoherence effects, we can create a qubit which is isolated from a source. Like putting one, there was nothing, and now we isolate a single electron, and the rest of the background of this molecule is completely inert. All right. Magnetism and correlation. There was something here that's in this diagram of total spin as a function of number of electrons, which was very interesting. Namely, when we had a spin polarized system, so maximum spin, yes, and we added one electron, we melted the spin. We lost this spin polarization. Just adding one electron. So here I was talking about the bilayer using electric field, very robust behavior. What we see here is that even if I take a single triangle and now I add additional electron, there we didn't add any electron. We just move electrons from one quantum dot to another. Here I am charging the triangle, and I see that there is no net spin. How can we understand this? So this is a little bit like rapid depolarization in the quantum Hall effect. When you look at the nu equal 1 state and you move away from it, the spin polarization decays very rapidly as a function of number of added charges. So we start with this spin polarized state. I can only bring a minority spin electron. I put it in, and then I want to see other spin up electrons. So I sit on this electron, okay, I put it here, and I look at the all other electrons with the same spin. And if this was the configuration, my pair correlation function would give me 0. There are no other spin up electrons. Yes? This is obvious from this picture. But then I turn on interaction. And what happens is that there are a lot of spins that have partially turned around. Okay? So my ground state is highly correlated, and there are as many spin up as spin out electrons. So there's no net spin. I turned off the spin. I have no other better way of doing this with my finger, but just showing you the effect of electron-electron interaction as seen by this pair correlation function. Because when the system is spin correlated, strongly correlated, it's difficult to add electrons to the system, and so you have spin blockade in transistor. Photonics. So we need to satisfy three functionalities. Let's again do this with the triangle. We need to show that we can make absorb light by making transition from the valence band to this conduction band states or zero energy shell. So you need to calculate dipole moment for each of these transitions. And when we look at these states, the top of the valence band is localized mainly in the bulk, and the zero energy shell states are localized at the edge. And if that was the case, it would be hard to make optical transitions. But and so for such a state, the dipole moment is very small. But as we go through these states, we see that there are some states that have a bulk character, and then they give a finite dipole moment. So yes, the structure is active. You can collect all these transitions, and you can map out the absorption spectrum. Now, we can connect the magnetic properties and the optical properties, and in the last 2 minutes I will just try to explain how this works. So imagine that I have my triangle. Okay? The electrons of the zero energy shell are spin polarized. So this is an artist rendition of the spin polarization in this triangle. They are all sitting with their parallel spin. And now I bring a gate and I melt this spin polarization. So I bring in additional electron. I now turn on electron-electron interaction, as if I could. And this spin polarization in the presence of this extra electron has melted. So I don't know, we visualize this by showing spin up and spin down and spin up and spin down. So the net spin, when you add it up, should add up to zero. So I melt it. And now I illuminate my quantum dot with a photon. And what this does, it creates an electron-hole pair. Okay? So there is a hole here. And I need to turn on final state interactions. So I need to turn on interactions with this hole. And this hole has a magical effect when this hole acts in the same way as a field marshal entering a room full of soldiers. When the field marshal enters, everybody stands at attention. And so all the electrons now align their spins to be parallel or anti-parallel to the spin of the hole. So we can create this magnetic moment, we can erase it with a gate, and then we can restore it with a photon. And I love if some of you could come up with something useful we could do with it. You can map out all the absorption spectrum of such a dot, and the interesting thing is that you can actually measure the magnetic moment by the absence of terahertz absorption in the terahertz. All right. So I talked in this graphene stuff. I talked about an opportunity that exists, perhaps, to combine electronic, photonic, and magnetic properties in a single material system, nanoscale, the thinnest there is, and just doing this with lateral size, shape, and edge engineering. I think it's quite interesting, and perhaps we could make a quantum circuit out of this in the long run. As usual, there are some things that we need to do to get there, and that is non-trivial. We need to be able to fabricate in a controlled way these structures. We need to have a full control of the edges. And then we need to think of integration. How do we integrate these different elements, when quantum mechanical counting starts to play a role, and how this will work, I don't know yet. So, I talked about some of the challenges that we have, and I talked about some possible routes toward addressing these challenges, and I spent some time talking about electron spin qubits, yes, when we started with isolating a single electron field and building more complex structures, and perhaps building a macroscopic quantum state in a field effect transistor. And then I talk about new materials and about doing everything with carbon. And I will just thank my colleagues who contributed to this work, and thank you for your attention. Thank you very much.